No nation which expects to be the leader of other nations can expect to stay behind in this race for space.
Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Please don't forget to like and subscribe, and thank you for your support on Patreon. We appreciate you. Not long ago, we did a lesson on the amazing potential of rotating detonation rocket engines. Today I'm happy to announce that an American researcher working in Japan has made an incredible breakthrough in this technology. A breakthrough that could render obsolete every regular combustion engine on Earth today. Please pay close attention to this presentation given at the Advanced Propulsion Engineering Conference.
And then, let me see, Raviv Yatam and Chris as well. Okay, and so you had a presentation, Will, and you have two colleagues with you. So do you want to start the presentation? How should we do this? I can put up your PowerPoint if you like. Oops, your sound is turned off, sir.
Sorry.
There we go. Okay, no, you're fine.
So I'll start it, then I'll pass it off to Christopher. He'll pass it off to Raviv, and then Raviv will pass it back to me.
I'll leave all of you gentlemen on the screen then, and I will hide myself. And then when we get to the videos, I may owe you a tremendous apology. I'm still learning some of the in and outs of StreamYard myself. But hopefully we'll be able to make that work. And again, thank you so much. Again, you guys are actually building things, doing experimental work, and it is brilliant. So this is the hybrid rotational detonation engine, right?
Yes, that's right.
Okay.
Yeah. So, okay, go ahead. Oh, okay. So I'm introducing our work for the multimode RDE, which is a rotational detonation engine. So this technology is rather new and is disruptive, but it's for affordable, high Mach, long range transportation and recreation and other uses. A rotating detonation engine, RDE, is a more compact and efficient method of creating thrust for various transportation systems. These are mechanically simple engines with no moving parts, which makes them less complex than gas turbines, also makes them lower cost and simpler to manufacture. RDEs RDEs burn fuel supersonically using traveling detonation wave and delivering high performance in a small volume. Volume savings also contribute to increased fuel and or payload volume, meaning that you can trade off the volume of your payload or your volume of your fuel because they're extremely efficient, providing potential range, speed, and affordability benefits compared to rockets, ramjets, and gas turbines. These are organizations that are currently studying RDE, but there's actually several thousand universities and companies around the world that are actually studying rotating detonation engines. So you see the same companies as I showed before, and the materials they use, the types of fuels. Hydrogen and methane are actually the top two choices of fuel. And you see the engine types that they're working on and the challenges, but it's all research. There's no practical rotating detonation engine available in today's market. There are generally speaking two types of RDEs. but both of them are toroidal, but they're either a continuous or a periodic type. So, and obviously the periodic type will have some sort of valve mechanism, usually a mechanical valve. But the key difference is efficiency or mixing a fuel to get the right stoichiometric ratios. So breaking them down, there's yet another 4 types of engines under that class of engines, and they are the combustion chamber shape, the detonation propagation, the way that the wave travels, and the fuel injectors, which are either a gunpowder type of injector or spark plug type, which is electrical. The advantages of axial are simple design. Annular has a better combustion because of the mixing efficiency. Multiple inlets types also have good combustion and some improvement in efficiency. Coaxial, better control, but whether or not the efficiency is actually improved is academic. So this is a video that we have of the detonation wave, how it propagates. And then the second half of the video is to show you the demonstration of the RDE actually working. In fact, an RDE of one of our collaborators. And let me see if I can do this. No, cannot do that. So can I do this? No. Oh, I actually uploaded another one, but it didn't work. Okay. So I guess we will not be able to see this video.
Here the good professor had some AV problems with the host's new software. That's to be expected. We were able to get it working here at the Academy, and we'll play it for you now. What you are seeing is the wave of combustion moving through the fuel and oxidizer vapor cloud. This is probably hydrogen gas, but this technology works fine with methane and other fuels. A major benefit of a detonation engine is almost complete combustion of reactants, about 99%. Another is that the ignition wave is moving at supersonic velocities. Regular rocket engines try very hard to prevent detonation at all costs, as the advancing shock wave will destroy most of them. These rotating detonation engines have been designed to survive and harness the power of the detonation wave, which is what gives them so much thrust and efficiency. Some of you will remember that NASA has also successfully tested an RDE recently on the ground. But understand that these rotating detonation engines from Japan have already been tested in space.
Yeah, Will, sorry to jump in. So you do have a couple of documents. Let me know if you need me to switch those also. Looks like you do have another.
Yeah, I actually have this video in a PowerPoint.
Okay, let me add that to the stream. We'll give this a try. Let me remove the slideshow for just a sec. Okay, and we'll add the video, and we'll cross our fingers.
Yeah, it uploaded, but
it's not letting us play it.
Doesn't seem to be working. So I don't. Yeah. Okay. What should we do?
Yeah. Well, let me. I'll remove that one. I'll put the PowerPoint back up. Let me apologize to you. This is we're still figuring out some of the bugs.
Okay. Well, this would have showed the actual detonation wave, and it would have shown actual working RDE, in which our early designs were actually based on. So, so I looked at the TRB because of this group, and I wonder if when the RDEs are at a distance, they actually look just like these pictures. So I don't know. I have no proof one way or the other, but our TRBs powered by RDEs, because RDEs are the most powerful engines known to man at this time, and they have the capability. They actually have the same capability as being able to lift very heavy objects uh, with a very high efficiency of the burn rate. So therefore, technically, an RDE could actually drive these types of craft. Okay, now I want to introduce Cochrane exploration.
Thank you for the introduction, Dr. Rankin.
Yes.
I don't know, will the video play, or if not, I'll see if I can share my screen.
Does it look like it works?
Let me try something.
Tim, do you need to adjust this so he can show his screen?
Yeah, I'm trying to share the tab now.
So let me see. It looks like his slideshow is up. Yes, I think that I do need to. Do you? So you're trying to show the tab. Is it having problems, Chris? Let me
Nope, it looks like it's showing on my end. I just need to
try and click the present button.
actually let me stop sharing. Let me try again.
Okay, and let me see. Is there a little light bulb on it? I see one with that Raviv has added.
Yeah, maybe you can use this one if you can.
Yeah.
I'm not sure.
Would it be this one?
No, not this one, but the other one,
Okay.
the video file.
To advance science and industry into space, the world needs safe, fully reusable
fine.
access to orbit. To accomplish this goal, Cochrane Exploration has been developing the CX-01 orbital spaceport.
Chris, you want me to mute it?
This is the first iteration
No,
of
go
a
ahead.
large-scale, horizontal takeoff and landing direct-to-orbit platform that will revolutionize the space industry. It can transport cargo and passengers to low Earth orbit, as well as providing a crewed laboratory and orbital manufacturing facility. Orbital laboratories also allow the development of medications and alloys not possible on Earth. The concept of a single-stage to orbit spaceport has been around for a long time, but new advances in propulsion and metallurgy make this design not just possible, but optimal. These ships can be flown autonomously or with onboard pilots. They use air-breathing engines burning liquid natural gas to achieve high-altitude flight and velocity, then fire advanced rocket engines to launch themselves into orbit. This same technology allows an active cooling system to absorb and reject the heat of re-entry. The Cochrane design profile allows the ability to lower pre-built laboratories, industrial facilities, and habitats into the ship for transport to and from orbit. A ship with these capabilities will be vital to the development of large orbital space stations. They can also be used to safely transport passengers and cargo for point-to-point terrestrial destinations, allowing vital supplies and personnel to land at any major runway on Earth in less than 2 hours. The new age of space exploration has started, and the Cochrane CX-01 is ready to speed humanity's expansion into the new frontier.
I hope you enjoyed that intro. Welcome to Cochrane Exploration. Our goal is to make space accessible to everyone. To do so, we need to solve some problems in our industry. High launch cost, access to only a few, vehicle safety, reusability, and accumulated space debris obstructing orbital wings. Our solution is our direct-to-orbit platform, which uses multiple engine configurations and operational modes to achieve spaceflight and other various mission profiles, such as point-to-point transport, onboard manufacturing and lab experiments, and longer-term space exploration. For size comparison and reference, you see our Terran, Lunar, and Demo class vehicles compared to an Airbus A380. The primary difference in topologies, other than size, is the Terran class is the crewed variant of our vehicle lineup. As you can see in this overview of our horizontal takeoff and landing flight profile, we're using our methane-enabled air-breathing RDE cluster for atmospheric flight. Once at altitude, our vehicle transitions to the onboard RDE array for orbital insertion, spaceflight, and powered re-entry. Finally, this overview shows callouts for the aero surfaces, solar array, metal matrix ceramic heat shielding. You can also see the air intakes used to power both RDE clusters, which also provide fuel for the RDE array.
So thanks again for having us be a part of this. We're really excited to work with Dr. Rankin and True 2 Materials and Mir Holdings, and just using their technology to implement in our vehicle lineup. And so with that, I'm going to turn it over to Raviv Yatun, CEO of Mir Holdings.
All right, thanks a lot. And Tim, if you can move me to the slide.
Absolutely. And, you know, I was just saying in chat, Chris, that is an amazing presentation. That absolutely, it's so powerful. This is so powerful. I mean, just congratulations.
I've got a good team working with me, so yeah, I'll thank them.
Well, and in if you're open to it in the future, maybe you come back and present on your own as well. I would love to have you present more and go more in depth. Okay, so let me turn things over to Raviv and okay, and sir, should I add this one to the stream?
Yeah, absolutely.
Wonderful. Okay, and just let me know, you know, what you need me to do in terms of the PowerPoints and when you need me to do it.
Sure, I'm on it. I can move the slides as well. So thanks a lot, Chris. And I'm working with William together. Lucky enough to work with him. And together today, I'm going to talk about two aspects which are not necessarily connected to Chris here, but I think they are valid and important. And the first one is the ability to generate greener energy. And in that sense, we come with a great efficiency and with the ability to have less carbon footprint or any other pollution type of pollution. So we're talking about much lower emissions and a very efficient system. And obviously, we all think about going out into space, but there are a lot of problems today in our world that we may address using those great technologies. And we're absolutely thinking about the idea of generating energy using it, or even using it for other transportations, not necessarily for aerospace, but maybe even water or a ground transportation. So that's one aspect. And the other aspect is the ability, how can we actually generate energy as we move and can we actually do some instant fuel generation? So imagine the following: can we actually go off from Earth, and while we're traveling to space on the atmosphere, can we harvest the needed gases in order to use our fuel? And in our vision, we see a situation where we actually leave into space with a full tank. So the ability to actually harvest energy as you move through the atmosphere. We also have activity in Israel, where I live in. I come from Israel. And this is an amazing technology, and there's a lot of excitement here, and we're also planning to manufacture some of the engines here in Israel. William, back to you.
Okay, Tim, can we go back to the presentation?
Okay, sorry. And I think that's yours, right? That's your
Yeah.
presentation, Will. Okay.
Is this it?
Yep.
Oh, yes, it is. Okay, got it. Thank you. I didn't realize we were already back. Okay, so what is different about our engines and why we are already in the commercial sector is because we've been able to solve the heat problems and the other problems that rotating detonation engines that no one else has been able to solve. So we've built new engines that are more efficient than what has come before. They're compact, they're solid state design, they have no moving parts, they are recyclable, we have efficiency through detonated combustion. In fact, we have the most efficient combustion process and higher specific impulse known. Achieving more thrust with less fuel consumption, lowest in range of size of jet or rocket engines. We use laser ignitions for our engines. The small size provides more room for fuel and payload in a given airframe size. Reduced size means greater loadouts. Highest specific impulse and thrust, misspelled that one, in industry. Technology to engage, which gives technology to engage a wider range of orbits. Today's rocket technology is very limited to the types of orbits it can achieve. So with rotating detonation engines, we changed that. Far superior to normal jet or rocket engines during operation built by Pratt & Whitney, Lockheed, or even SpaceX. So we're superior to even SpaceX and Lockheed and Pratt & Whitney as far as technology is concerned. The time between overhaul and maintenance is the lowest in both rocket and jet propulsion industry. We are 5 to 10 years ahead of all competitors in delivery to market of hundreds of these engines during 2023 and thousands available in 2024. I believe we had a very nice video here, but unfortunately it looks like we can't actually do that. Perhaps next time. So what I like to show here is that we have we can of course make our engines in virtually any type of material. So, but we currently have a range of materials from thermoplastic to stainless steel, the Inconel, the titanium, and then we have nanoceramic matrix, metal matrix materials, which were developed in my laboratory. So, but what I want to show here is that we also can bring to market materials that fit into practical markets for RDEs for different types of applications, including shipping, recreational sports, yachts, power stations, aircraft, and space applications, and more. Um, so, in general, what is a RDE? So, an RDE is you have, right? Okay. So I guess I don't have. Tim, is there a way I can point to stuff?
Oh, is there a way that you can use a pointer?
Yeah.
I am not sure. I don't think so, unfortunately.
Okay, that is fine. I will try to do it with that one. So, okay, so RDE is made of typical materials. Generally, an RDE has oxygen input and a fuel input. The fuel can be virtually any type of fuel. And then it goes up the base and into a nozzle system, which then has an igniter near there, which then ignites the fuel. The propagation of the wave is rotary propagation rather than a propagation that goes across, that goes out the thrust like a subsonic flow in a normal rocket engine. This actually has supersonic flow from the very beginning, all concentrated and focused into a central point, hopefully, because then you don't actually eat the walls of your engine. So this wave travels at 2,000 meters per second, generally. And in the case of this particular example, 500 newtons of thrust are produced for 2 to 6 seconds. And at around 7 seconds, it starts to go into meltdown. A RDE with typical cooling requires a way to cool it. Then longer time to meltdown, but less than 100 seconds of operation in general, because these things are extremely hot. So with our advanced ceramic materials, we have no cooling, and we withstand temperatures up to 3,400 C. We have multiple restart, lightweighting, because we use 3D printing, increased performance, heat management, over 200 seconds, no meltdown, and optional thermoelectric energy scavenging to support to support in any type of DC circuit that is on your platform. So we are working on engines in these ranges. So the largest is 16 centimeters tall. It's 12 to 18 centimeters in diameter. We have 3 centimeters and 5.5 centimeters and 2 centimeter diameter. In these for larger rockets and ships, you would use the larger engines, We have drones that we are working on with other people. We have also small boats and drones and other rockets. And we have kinetic projectile Mach 2 that operate at Mach 2 that are only 2 centimeters in diameter with a 10-kilometer range. So, and other types of space assets that are under development. So these are the ranges of sizes that we typically produce, because these are the most efficient sizes for this type of engine. We also partnered with established companies who design and build laser windows. These are examples of laser windows that we have been working with. We also have HIPS manufacturers, which we also work with. So these allow us to ensure that the uniform crystal structure of the engine is actually uniform. And if there's any dislocations, then the HIPS will help us to fix those problems. So currently we can manufacture 300 engines per month. They have with hydrogen, oxygen, and methane, they have a 99% efficiency of operation. And in next year, we are planning to go into 9,000 engines per month in 2024. We have our specific impulse and thrust of two-tube material operational RDEs are more efficient. We have the highest ISP factor in the industry. The lowest ISP factor in the industry now includes SpaceX, Blue Origin, ULA, Aerospace, Rocket Lab, Boeing DSS, OSC, Virgin Galactic, the Chinese, which is CGWIC, Relativity Space, and even the United States Air Force. So I plan to have a part 2 later in the year for this presentation. So I hope that by that time a lot of the video stuff will be fixed. So Tim, back to you.
Awesome. Thank you. And actually, I am just updating our presenter instructions so that we don't run into the video issue next time. So Will, I've done some research. It doesn't look like there's a pointer tool, just so that we know for future presentations. There's no pointer, okay, unfortunately. And actually, Chris solved this. You can upload videos, but we can't do them in PowerPoints. So, you know, I'll make notes on that. Yeah, and let me apologize to you sincerely. So I think if you're all done, let me see. We have a lot of time for Q&A, but let me do this. I want to let me close down the slideshow there, and I'm going to bring everybody else back in. Let's do some Q&A, guys. But first, before anything else, I want to give all 3 of our presenters an enormous applause. So Dr. William Ryken, Chris Obafunwa, and Raviv Yatam. Gentlemen, thank you so much. And just absolutely amazing technology. Absolutely amazing. Again, let me apologize sincerely for the video issues. I feel like every time we feel like we've mastered something, we run into something else that we don't know. So, and Chris, again, the video that you did that's inspiring. It's absolutely amazing video demonstrating this technology. So guys, let's do some Q&A. Who wants to go first here? We can go through chat as well.
I have a question for them. I just briefly looked up what a pulsed rotating detonation engine is, and there are a couple videos on it, but I guess you guys are having trouble with your videos. Can you explain why this is putting out a higher ISP than a regular rocket engine, and what the power levels that you're achieving are, like the thrust?
I can explain a part of that. Some of it's actually proprietary, but essentially a rotate detonation engine is a supersonic engine that concentrates the energy in a very small space, given a very powerful thrust. The problem with the typical rocket engine is actually subsonic flow coming out of the injectors, whereas the RDE has the supersonic flow coming out of its injectors. So therefore, you don't see, you see our nozzle is very straight, but you realize that the bell nozzle is required for a rocket engine because it has it requires that throat in order to convert the subsonic flow to the supersonic flow. The problem, one of the biggest problems of Bell rockets is that it has a lot of multiple frequencies that are jamming each other and actually destroying the efficiency of the burn. So you only get, I believe SpaceX probably has the highest efficiency. I forgot what the number was. It's pretty good. But the typically a rocket engine is going to give you about 30 to 40% efficiency in the burn of the fuel, which means all the other fuel is just going out the back. So whereas a RDE has a very high burn efficiency of up to 99%, where, you know, which is what I was explaining. So because it can burn such a high efficiency, it uses a much lower amount of fuel to generate thrust, whereas the bell-shaped rockets requires so much fuel just to get a percentage of thrust that would actually move the rocket. Does that make any sense?
Yeah, it does. Another thing that I saw online, this is from the people who research rockets, is that it has these rocket engines usually have pretty low specific total thrust. Is that an issue that you've come across as well?
You mean RDEs?
Yeah.
No, that's not our. That's not our. We don't have that issue at all. If anything, for the, you know, we have, for example, we have a 750 gram rocket engine that can fit in your hand, that actually outputs between 50 to 500 newtons of thrust.
Yeah, that's kind of what they were saying. 500 newtons is like 50 kilos, right?
Yeah, but it fits in your hand. Now, if you want a 500 Newton jet engine, it's about 2 meters long, about a quarter of a meter diameter. Okay, and it will burn 30% of the fuel. So you need a big gas tank. I can do the same. I can do, you know that little example I told you, fits in your hand, gives you up to 500 newtons of thrust, which is not actually, which is the same amount of power as the turbine, the jet engine that I just told you about. Now, I know this because we've already done that study on comparing the jet turbine, which is used in drones, to our tiny little engine, which can fit in your hand.
Will, I have a question for you. First off, amazing presentation. So you had two questions for it. First question, you had some numbers for how many engines. Oh, sorry. You had some numbers for how many engines you guys currently can make, as well as projected numbers of 300 this year and 9,000 next year. I have to assume that like the sizes of those engines aren't like to orbit sized, right? Those are like smaller model, like minisat sized.
No, these engines, we produce a range of sizes. However, the engines that we produce can actually do SSTO. And in fact, Chris's vehicle will be using those engines.
Excellent. Second question. Your payload capacity for these things. Are you thinking that this is going to be solely for orbital missions, or might this be useful for lunar missions?
I see no reason with the ISPs that we can produce with these engines that you can't do SSTO to and then move on to the moon from there. So, and one other thing is you might have noticed the thermoplastics. So the thermoplastics that we make are extremely high temperature. So we've designed a thermoplastic in which will in the $40,000 range, which will allow us to bring to the market next year an RDE which can do SSTO, which is single stage orbit, for small payloads. So that way, people who are entrepreneurs who want to start building their own platforms, their own rocket platforms to launch small payloads into orbit will actually be able to.
Well, Will, if I could jump in with a question. So one thing I've seen in the past is SSTOs based on concept fusion drives, right? And
Sure.
Is this something you think might be integratable with that? I think when I believe it was Jared had asked about like potentially going to the moon with this, right? And the past SSTO design that I saw, this was many years ago. Dr. Paul Siz had talked about that, a lunar, potentially even Martian transport, right, based on a fusion drive. Do you think that you could use the hybrid rotational engine in conjunction with something like that and switch to that once you're in space? Or,
Well, I have never really looked at the problem from that perspective, to be honest. But if I was just talking off the top of my head, which I am, then I would say that why fusion drives are so popular for these things is because of the very high ISP. So if we already have a very high ISP, then if you need to get them into orbit, then this is the platform to do it with. So, I mean, we're at least 40% 40 to 50% better in producing thrust and impulse to than SpaceX.
yeah, well, that makes sense. It's incredible technology. Thank you so much for presenting this for us today. It's absolutely amazing.
Can I get a question in? You have time for that?
Yeah, go for it, Chance.
Hi. Well, just first of all, amazing and inspiring presentation as we see you're kind of moving to that level of vehicles that can fly, and then I want to make sure I'm getting that right. Is a vehicle that can fly into space and return and be reusable, and you're not
horizontal takeoff and landing.
you're not dumping stages and for fuel like you do with conventional rockets. Sort of reusable aspect as well. So I can definitely see where if you're a smaller engine, your efficiency, fuel utilization efficiency is higher, then you more fuel will get you farther. So you do have so I just wanted to verify that this is a vehicle that would take off and land and be reusable, but can go into space.
That is correct. That's the whole objective.
Oh, that's so cool, man. All right.
So, by the way, I just want to say, thank you, Gary. I really did like your presentation. Actually, I specialize in below 5 nanometer production of materials. Actually, we're actually in the angstroms of actually atom to atom and manipulation of atoms to actually create what we want to create.
Oh, so
we can make the atoms do what we want them to do. So we actually do that every day. So I was impressed by what you had said. I had not looked at inference patterns down at the atom level like what you were doing.
Thank you. I appreciate that. Again, like I was saying before, I mean, collaborating and working together, that's the way we're going to do this stuff. So.
Well, send me an email and let's chat on that.
I connected with Chris, and if he'll share the rest of you all the email, I'll be happy to keep talking.
Yeah, I'll definitely do that.
Well, and if I could do my pep talk thing, that's one of the things. It's not just APEC, but one of the things that I'm finding is, in terms of a core community, our email list now I think is probably approaching about 2,000 people, but really we picked up probably about the first 1,000, and that's probably about the core community that's involved with this kind of research. And it doesn't mean that there's not interest elsewhere. There are tons of interest. I mean, just look at the viewership for programs like Star Trek and Star Wars, readership for sci-fi magazines and novels, things like that, right? The entire human race is interested and knows. But when you look at the people who are actively doing work in this area, it is a small, tight-knit community. And so one of my absolute hopes is just to be able to help build collaboration. I mean, I think that's so important because together we are so much more than apart, and we're out in front of what traditional organizations like NASA and SpaceX and like those are doing, and that's okay. It's fine to be out in front, but it means that we just have to rely on each other more than ever.
William, somebody has a question here. If 700-gram engine can produce 500 newtons, what size fuel tank is needed for propulsion? Would it actually take off?
Well, it depends on the mission profile and the type of fuel you're using.
Fair enough. Have you also considered doing something like Virgin Galactic, where they have an airplane that takes it up to 30,000-40,000 feet and then drops it, and it goes the rest of the way up to orbit?
Yeah, well, I think that idea is actually a good idea. I don't have any opinion one way or another. These ideas have been around for a long time, and I'm happy to see their success. But no, we're happy to work with anybody who anybody who wants to work with us. We're very happy to work with them. So,
well, speaking of which, and I have your guys' emails, but do you have websites or anything like that where folks can reach out if they have more questions?
I don't.
Okay.
So just email. So,
I have a question.
Yeah, Michael, go for it, sir.
So, Will,
Hey,
I'm
Mike.
curious. I'm curious. When are you going to have a toy version of this? So, and how much will it cost?
I have no idea. I've never thought about a toy version.
Like a
'Cause I
drone?
want
Are you
one.
thinking of drones?
Whole nother
Yeah,
market.
like a drone.
A drone. I've killed 2
Oh.
drones this week, so that's
Oh,
scary.
Yeah, so you need to keep the price low and the parts reusable.
well, actually, one of my pet projects is, pet hobbies is actually drones as well. I have DJI and Parrot, and I like them both. But Parrot has hyperspectral camera. I like that best. So, however, and it's 4K. Yeah. So,
Oh,
but
you know what? Well, I'm
I
going to
would
ask
like,
you about that.
yeah, I would love to have
Just a thought.
a drone using these engines, but I haven't found the time to do it.
So
Well,
this
you're
week,
in the size range. It seems like it's. Can you make it smaller?
Yeah.
Is what I guess.
That's a good question, and we've partnered with some companies to look into that, but we haven't really gone through the cycle to get them all together and actually try it.
Well, that's a good way for people to learn about the tech. That's for sure.
Definitely. I look, if we make a rocket powered drone or jet, I should say rocket and jet, because this engine can use atmospheric oxygen as well as pure oxygen to operate. So we're not limited to rockets. We can actually function as a jet engine as well as a rocket.
Yeah, it would be a great toy. That's all I could say.
And for Birdie, I would say we already have a lot of operating RDEs. So when can you see it? I have another presentation later in the year that Tim and I have been talking about recently, and I'm hoping that we will do it at that time.
Wonderful.
Thank
And
you
again,
also for your presentation.
Well, and Michael, thank you. Sorry for interrupting. So we can do, well, if you want to give it a try, I don't know if you have an independent video file that you can upload. And if you want to, oh, okay. Do you want to try that? Try and do upload. So if you go to the present button in StreamYard, and there should be a video file. I think that was what Chris did for his.
Okay, let me find cursor. Sorry, I've got 2 screens here. I got to find the cursor. Okay, video file. Yes.
Yeah, and then I think you just select that. Let me see. Yeah, you just select it from your hard drive. And so we may be able to see your videos that way. And again, let me apologize for the PowerPoint bug there.
Let me see. I'd like to show the detonation one. So where did I put that?
And I'm going to follow up with you on the Parrot drone thing afterwards. I had one. I learned the hard way. Fortunately, it was super cheap drone. I was practicing. Do not use a drone on the beach with crosswinds. So I got it up to about 40 feet in the air. Oh, it was beautiful. I had my little 720. Again, it was super cheap drone. Little 720 video. I'm practicing with it. And then I watched as it just drifted out to sea. I have it up on my Facebook. I was just like, bye-bye, little drone. Bye-bye.
I'll just see. That's not cheap. I paid $2,500 for mine. That's not cheap.
Yours could probably fight the crosswinds. I had a little, mine was like a $80 drone, and I did that on purpose because I have a talent for killing them. Walls, buildings, trees. So
Okay, so Chris, I tried to upload that video and it says the video file doesn't have a video track. That's strange because it works as a video.
Question, Tim, can you play something directly from YouTube on your end?
I think so. If you want to give me a link.
Private chat.
I will drop the link in the chat and let's see. And this just kind of shows the use cases for RDEs. Hopefully this works.
Yeah, actually, me and Raviv were talking in the private chat. I'm actually flying out to Israel later this month, so I might go and meet him in person.
Amen. Hallelujah.
Okay. Oh, there we go. Okay, so Chris, let me bring this up in a separate window. And if you want, there we go. Okay, and this is called Dr. Riken's video. Oops. Okay, and there we go. I'll put that in theater mode. I'll press play.
I don't think the audio is coming through.
There's no audio.
Oh, okay. Then we can talk over it. William, what is the specific impulse over using the same amount of fuel in a RD versus a regular rocket engine?
I think I need a lot more information than that.
Okay, like let's say you have 10 kilos of fuel in outer space. What would your meters per second velocity change be in RDE versus a regular rocket engine? It would be like 2 times more.
We don't even know what kind of fuel you're talking about.
Similar types of fuel, a hydrogen oxygen mix, or fuel being the same. What would the specific impulse increase be?
Okay, wonderful.
Okay, you want the specific impulse?
Are we orders of magnitude more powerful, or is this an increase of 30, 40%, something like that?
Yeah,
What
if
are
you do,
trying to ask?
well, let me jump in really quick. So if you do have more videos like that you want to play, yeah, YouTube is easy. If you have stuff on YouTube demonstrating the effect or anything like that.
Oh. Yeah, I don't have anything on YouTube.
Like a regular rocket engine for 10 kilos of fuel puts out, X amount of newtons for that long. That will give you, a certain amount of movement through space, meters per second of change. What would a pulse detonation engine do better than that? Would it be 2 times better, 10 times better, 40% better, 10% better? Like, can you give us an idea of how much better it is?
That's not a good way to compare them. To start with, there's a lot of missing numbers here. So, like I was saying in the presentation, I was explaining what we can do, but if you push the pulse detonation engine, and it's the right size, has all the right characteristics, then you're looking up to around 6,000 ISP for a pulse detonation engine. And there is no rocket engine anywhere that can do that.
Okay, so 6,000 ISP versus,
I mean, you're looking like, I think the most efficient rocket, I forgot who makes it, is like 350 ISP or something like that.
So it's roughly about
So-
20 times better.
Well, take it for what I just said.
Yeah.
You're
So
looking between 6,000 and around 350 for the most expensive and most efficient rocket today.
And Mark,
Something
Mark,
like
keep in mind that it is the
So-
absolute middle of the night, Will's time. So math is not probably his top thing at the moment.
well,
It's-
that's a major increase in ISP. We're talking roughly 20 times better. Raviv, is that correct?
Yes, that's correct.
Well,
Yeah.
gentlemen, we're at the top of the hour, actually. So why don't we do this? Why don't we give Dr. Will Riken and Chris Obafonwa and Raviv Yatam a giant applause. Gentlemen, thank you so much. Let me apologize again for the bugs. We're still getting used to StreamYard. Still absolutely brilliant presentation. Absolutely amazing videos. The technology that you guys are working on is tremendous. And Will, I would love to have you back. And actually, I would love to have all of you gentlemen back, either together or separately in the future. Again, absolutely amazing technology. So, okay.
Yeah,
Well,
it is very amazing technology, and it's something that should be developed as much as possible. So, but I'm really rooting for the little guy to get into the rocket business, and not just big multinational conglomerates like SpaceX and Blue Origin, or you don't have to be a billionaire anymore to go to space, is what I'm really saying.
The technology behind rotating detonation engines is described fully in this lesson. If you haven't seen it, make sure you do. This is the future of chemical rocket engines, and has the potential of finally giving us personal flying vehicles and single-stage ground launch to space and return technology. Right now today, with a continuous specific impulse of 600 seconds and a pulsed specific impulse of 2,000 seconds, combined with an amazing thrust-to-weight ratio, all while maintaining high mass propellant flow, this is the ultimate chemical rocket engine technology. Nothing but nuclear technology can even hope to compete. And we'll give you an update on that science next time. Until then, thanks for watching, and stay safe. At Astra Pro Terra.